Hi all, welcome to the Week 3 reading guide for ENVI 211 online in spring 2017. We're going to be talking about various aspects of the atmosphere, ocean, climate, and weather, and some natural hazards this week. Hopefully you've already read the chapter in your textbook. I'm going to just pull out a few important concepts that I want to make sure you understand how they link together, because the book, I think, treats them all somewhat separately, and I want everyone to understand how all of these aspects of our natural world are, in fact, interconnected. So first of all, we've got our atmosphere. This is directly out of your textbook. I do want everyone to be sure that they understand how the atmosphere is layered. So that's important in terms of understanding how atmospheric properties relate to our wind and weather patterns. Our weather mostly occurs in our troposphere, which is the closest layer of the atmosphere to the Earth. The ozone layer, which we've heard so much about in terms of it being thinner and thus contributing to our UV exposure, that is in the stratosphere, which is the next layer up. Then the mesosphere, the thermosphere, and of course, eventually outer space are stacked on top of that. So if you think about the atmosphere, think about all of those gases weighing something and pressing down upon a surface of the Earth. One unit of volume of the air, that column of air, is going to have some weight on the surface of the Earth. And so when we talk about air moving from high pressure to low pressure in subsequent slides, you'll understand why that atmosphere has pressure. It's a column of air pushing down on the surface of the Earth. So Earth's atmosphere is really different than nearby planets. Why is this? I don't know if anybody's ever wondered this, but the reason is because we have life on Earth, and life in particular uses and produces oxygen more than would be expected if we had no life on the Earth. So basically, early on, organisms were not oxygen breathing or utilizing, and so everything was anaerobic. No oxygen. Over time, we had organisms evolve to undergo photosynthesis, and basically that has resulted in adding oxygen to the atmosphere. So plants, which are of course the largest element of our food system or food webs, right, the cornerstone as producers, so we have more plants than anything else in the world, but most of those plants are undergoing photosynthesis, which is adding oxygen to the atmosphere and removing carbon dioxide, and this effectively changed our atmosphere over time as Earth and life evolved. One thing I want to make sure everybody understands is that part of the reason the planet is actually livable is because we have greenhouse gases in our atmosphere. So we've been sort of taught in this age of climate change, which we will discuss later in this class, we've been taught to think that greenhouse gases are bad. However, I want to make sure everyone understands that greenhouse gases are a natural aspect of our environment. And what they do, basically, is allow the incoming sunlight here to filter through the atmosphere, hit the surface of the Earth as light. It's re-reflected back as heat, which is the red arrows in this diagram. The greenhouse gases in our atmosphere here are basically absorbing that heat. So sunlight coming in hits the surface of the Earth as light, re-reflected as heat. The greenhouse gases absorb some of that heat and then re-reflect it back out to the surface of the Earth. And that greenhouse gas effect is what keeps our planet livable. If it were not for that effect, we would be living in a very, very cold, like negative 30 degrees Celsius planet. Not very hospitable. We could do it, but probably not conducive to life having evolved. So this greenhouse gas effect is what has enabled us to evolve on this planet, to live on this planet. However, what's going on with climate change, which we will talk about again down the road, is we've added additional amounts of greenhouse gases to our atmosphere. So this capture of this absorbent or capture of this re-radiated heat energy is increased today. And so that means that the atmosphere, unless the surface of the Earth are heating up faster than they would be if we did not have as much greenhouse gas levels in our atmosphere. The other thing I want to make sure that everyone understands is the concept of what creates weather and climate. So we're going to differentiate between weather and climate shortly, but in terms of understanding how where you are on the surface of the Earth determines what the temperature and precipitation conditions are like, which then goes on to determine what life can live there. This all relates back to two things. I'll say them now, and I have another slide that will show them very clearly. Uneven solar heating and the Coriolis effect. So, uneven solar heating. Why is it colder at the poles than at the tropics? So this relates back to our heat budget, which is the incoming energy versus the outgoing energy. And this, for any given latitude, is not necessarily balanced. So that means that not all of the heat from the sun that comes into our planet is re-radiated back out to either the atmosphere or space. Sunlight reaching polar latitudes is spread over a greater area, so there's less radiation per unit area. Near the poles, the light approaches the surface at a low angle. This favors reflection, which means less solar energy. Also near the poles, light must pass through more atmosphere to reach the surface because it's going at an angle, and therefore it's passing through a larger amount of our atmosphere, which absorbs some solar energy and therefore translates less onto the surface of the Earth. So that looks like this, basically. Up in the poles here, say Alaska, the sun is low in the sky, a 1 meter square solar beam comes in, passes through more of our atmosphere, and then hits a larger area on the surface of the Earth. And that angle also favors absorption by the atmosphere of some of that energy. At the tropics, the sun is directly overhead. We have a shorter amount of atmosphere and a smaller amount of area over which that energy is being spread. So this square piece of land heats up faster than this patch of land here. And that means you have more heat at the tropics than coming in at the poles. Also, poles have more variation in day length. We all know this because the Earth is tilted on its axis. So in the winter, we in Anchorage get 5 hours a day of sunlight. In the summer, we get about 19. Whereas at the tropics, it's about the same all year round. So roughly 12 hours a day of light, 12 hours a day of dark. The poles are also farther from the sun. Not much, but enough to make a difference. So if your sun's over here, and light energy has to travel this far to get to the pole versus only this far to get to the equator, that's enough of a difference to decrease the amount of incoming energy to the poles. And what does this all mean? This all means that the region right around the tropics, or the equator, has net heat gain over the course of a day or a month or a year, whereas the area by the poles here has net heat loss. So there's more energy coming in here than is outgoing, and there's less energy coming in here than is outgoing. So that means you get this net energy transport from the equator to the poles. And so that starts this flow of air, basically. So as warm air over the tropics rises, it expands. Expansion causes cooling, which then causes the air to sink. So basically, this is the tropics. The warmed air heats the ground above it. That warm air rises, the rising air cools, and is displaced by more warm air rising. And so it flows in a circle like that. As that air cools, it becomes heavier, it sinks, it goes back down to the ground again, and so you get these cyclical, circular cells of rising, expanding, cooling, and sinking air. And so over the course of the whole Earth, you get these big circulation patterns like this because of that net energy transport from the equator to the poles. So you have rising warm air over the equator, gets transported to where it can cool and sink, and then that flows back along the surface of the Earth here to where it is warmed up, rises, descends, cools, and so on over and over and over again. So you might expect that that's the way atmospheric circulation patterns work on our planet. Well, we also have this rotating Earth. So I'll let you read this for just a minute. This is a little Calvin and Hobbes cartoon. The dad comes in, Calvin's dad comes in and says, "You playing a record? I'll show you something interesting." And the dad says, "Compare a point on the label with a point on the record's outer edge. They both make a complete circle in the same amount of time, right?" "Yeah," says Calvin. And then Calvin's dad says, "But the point on the record's edge has to make a bigger circle at the same time. The whole side of the record gets to the other side of the record player at the same time, but the outside point is moving faster, even though they're making the same number of revolutions per minute." And the same thing is happening to our globe. If you think about a point in the northern hemisphere, say Buffalo, New York, which is where I grew up, and then you think of a point on the equator, say Quito, Ecuador, which is definitely not where I grew up. The point at Quito is moving faster because it has to go around the entire bulge at the middle of the Earth than that point at Buffalo, which has to go around a skinnier part of the Earth. So what happens is the Quito point is moving faster than the Buffalo point. And this translates into a trajectory of moving anything, a cannonball in this example, or a mass of air that gets deflected. That movement pattern means that the cannonball coming from Quito to Buffalo, or the air mass moving from Quito to Buffalo north, is deflected to the right. The cannonball, or the air mass moving from Buffalo to Quito, is deflected to the left by that rotation of the Earth. And this is called the Coriolis effect. So, between the uneven solar heating driving patterns of rising and sinking air, and the Coriolis effect deflecting those moving air masses to the right as they're moving north and to the left as they're moving south, you get this global circulation pattern. And we call these cells Hadley cells when they're just north and south of the equator, Ferrel cells when they're the cells above and below the Hadley cells, and then polar cells where they are right at the poles. And so this also means that these cells create gaps in between them. You've probably heard of the doldrums, which means a place where there's not a lot of wind because it's between those two cells. You may have heard these high pressure belts between the Hadley and the Ferrel cells, also not a lot of wind. And then the jet stream occurs here between the polar cell and the Ferrel cell, which explains why when it waves, like it's been doing in recent years, you get sometimes really cold air coming down from the polar cell and then infiltrating into the lower 48, and that's that polar vortex. Global oceanic circulation has a similar pattern, and it's driven by similar things, except in addition to the prevailing atmospheric winds caused by the uneven solar heating and the Coriolis effect, which shifts how those air masses flow. Other things that affect oceanic circulation are position of land masses and ocean water density. Salty, cold water tends to go deep, and warmer, less salty water tends to sit on the surface. And so depending on where that water is coming from and how long it's been sitting in the oceans, that determines whether it's going to be more deep or more surface water. And all of these things, global atmospheric and oceanic circulation, determine regional climate patterns. So where you are in terms of those rising and cooling air masses, and where you are in terms of deep cold versus warm surface water going close to the continent, that determines patterns of daily weather, which eventually becomes climate. So weather versus climate, everybody should know this intuitively, but obviously weather is what's happening on a day-to-day basis, right? And climate is what typical weather conditions characterize a point on the Earth's surface. So in this picture, one image shows a raging hurricane, and the other image shows a blue sky day in the tropics with a mom and her young son in a canoe. And if you think about what characterizes tropical weather, which one of those would be weather and which would be climate? If you answered the hurricane was weather, and the blue sky, warm, inviting ocean picture of the mom and her son as climate, you are correct. Typically, we think of warm, stable conditions in the tropics, but with occasional bad weather events like hurricanes. We also have larger scale weather patterns that are not quite stable enough to be considered climate, but they do influence global weather and ultimately climate patterns. And the most well-known of these is the El Nino phenomenon. And this is one that your book does talk about, but I want to just highlight a few of the main take-home points. So the top little image here in this video is a normal year in the tropical South Pacific. The prevailing winds in this case move warm surface water westward across the tropical Pacific, and it ends up in kind of a bulge over by Australia. This means that as that warm surface water is blown across the Pacific, there's an opportunity for cold, deep water with lots of nutrients to what we call upwell off the west coast of South America. Now, in a El Nino year, for some reason, we're not quite sure always why, those easterly winds that normally blow that surface warm water across the Pacific weaken. And so that water just stays right there along the west coast of South America, which means without the displacement of that water, this upwelling doesn't happen. And so you get this pattern here, the right or left-hand globe here, where you have a warm surface anomaly of sea surface temperature in the eastern tropical Pacific. Now the reverse of that is when you get really, really strong winds blowing that surface water all the way across towards Australia. You get an even bigger bulge here in Australia, and then you get a lot of cold water upwelling all the way across the Pacific. And that's called La Nina, and that's represented by the globe on the right here. And so basically, when we look at the right-hand column of this slide, the effects of El Nino on our northern United States weather can be pretty dramatic in that during El Nino year, you get this low pressure zone right over the northern Pacific, and you have a lot of warm weather in Alaska and northern Canada and on into the northern part of the United States. And the jet stream is kept north of that by that warm, low pressure block of water, of air. La Nina is the opposite. We get a more variable jet stream. We have a high pressure zone in the northern Pacific, and we get more cold, wet, windy weather here in Alaska and northern Canada and the northern U.S. So it really changes our weather patterns. And these El Nino and La Ninas have varying levels of strength. So sometimes you get a really, really strong El Nino and a really, really strong La Nina, and you have very, very distinct effects on weather over the rest of the world. Other times we have a much lower El Nino or a much lower grade La Nina, and so we have consequently much lower impacts on weather. Okay, that's all I have for this week. I hope you guys enjoy these reading guides, and let me know if you have any questions.